Hi, I'm Tim Lafferty, Product Marketing Engineer for Industrial Interfaces at Texas Instruments. Today I'd like to discuss how CAN transceiver parameters affect the total system timing budget. CAN designers must carefully consider delays because the CAN feature of bitwise arbitration depends on the precise timing between the nodes. At the beginning of each CAN message, the identifier field sets the priority of the message. If two nodes try to simultaneously begin transmitting, the node with the higher priority wins through bitwise arbitration. Lower priority nodes stop transmitting as they receive dominant bits that they did not send, alerting them to the presence of a higher priority message being transmitted. Because each node must monitor the bus for dominant bits from other nodes, the total network propagation delay sets an upper limit for how fast the nodes can signal and the maximum bus length. The propagation delay between two nodes is the sum of all delays in the signal path, including isolation, transceiver, and bus medium. CAN nodes must receive each other's signals, synchronize to them, then respond during the arbitration. So the total propagation delay is the sum of two nodes' one-way delay. Assuming that each CAN transceiver in a given network has a comparable delay, the total round-trip delay between the controllers can be expressed as twice the isolation delay, plus the transmitter delay, plus the cable delay, plus the receiver delay, and then twice that for both directions. There are 4 delays associated with the isolators to be considered during each round trip. Typical CAN transceiver solutions with separate isolation must use the worst-case addition of these isolation delays plus the delays through the transceiver itself in calculating the effective total delay. With a typical one-way isolation delay of 40 nanoseconds or more, this becomes a significant part of the total networking timing budget. A key benefit of the ISO1050 comes from the integration of all the timing specifications into a single device. Rather than 3 components in the transmit-receive path, each of which has a separate timing specification, the ISO1050 has a single delay number to consider for any path through the device. With a typical delay of 150 nanoseconds, including isolation, the ISO1050 reduces overall delay and allows for longer cable length, faster signaling, and more stable network timing budget. The ISO1050 is the first CAN transceiver with isolation in a single package, so it has advantages in terms of reliability, board space, and timing. Based on TI's proven CAN transceivers and best-in-class isolation technology, these devices can simplify your design for robust communications and industrial applications, medical, and many others. Here's the pinout of the ISO1050. You can see how simple the input and outputs are. Powered by independent power supplies, the controller side and the bus side of the chip are fully isolated with ratings of up to 4,000 volts in accordance with UL, VDE, and CSA standards. Isolation is required by many end equipment certifications and provides proven benefits in terms of noise immunity, breaking ground loops, and inherent safety. Another key benefit of the integrated approach is smaller board size. Typically, at least 2 separate channels of isolation are needed to communicate with a CAN transceiver. Additional components may be needed to establish fail-safe, monitor power supplies, and check device temperature. With the ISO1050, all of these functions are integrated into a single 10 mm by 10 mm package. In addition to simply saving board space, benefits of integration also include fewer components, simplified assembly, and higher reliability. Overall, the ISO1050 CAN transceiver with integrated isolation delivers a highly reliable CAN solution with improved timing in a smaller space. To learn more about this isolated CAN solution, visit www.ti.com/ISO1050-V.